So hello everyone. Today I'm going to present a framework to design non-diagonal adaptive methods for training large neural nets. And we will show that we can view Newton's method as a Gaussian approximation. And then we can use this connection to design new adaptive methods. So let's begin with our motivation. So neural net models are powerful, and we can use to generate amazing pictures, generate videos, and neural net models somehow can understand natural languages. However, they're difficult to train from scratch. So in this talk, we're going to present a Riemannian framework to design adaptive methods. Our framework allows to use a flexible preconditioned matrices. Both can be diagonal or structured. And also, our framework can allow us to using inverse-free and decomposition-free update schemes. And as you will see soon, that in fact, this is crucial to training a large neural net if we want to using a non-diagonal methods. Okay, so let's start with the first questions. Why do you want using adaptive methods? Because you can also use stochastic gradient descent, right? So at least this in 5 years ago, people believe that, at least they think that SGD is a universal optimizer because you can see that this is a convolution neural net. SGD outperforms NMW. Yeah, it's true. So it generalizes better than NMW on convolution neural nets. But if you look at modern architectures, such as transformers, so basically you can see that in this case, NMW basically outperforms SGD on transformers. So as you can see that this results, we can see that clearly SGD is not a universal optimizer. So nowadays, people try to understand sign descent. And because sign descent performs very well on transformers, and sometimes can even better than NMW. But how about in convolution neural nets? So you can see that, in fact, sign descent performs less stable than NMW on convolution neural nets. So is sign descent a universal optimizer? No. So the message is that there's no universal optimizer. So that's the focus of this talk, is about presenting a framework to design many adaptive methods instead of focusing on one particular optimizer. And moreover, adaptive methods are more flexible than sign descent and stochastic gradient descent. Okay. So now let's talk about some computational and numerical challenges to design adaptive methods. So to train a neural net, we often have to solve an unconstrained optimization problem. And the objective function often can be expressed as a finite sum of individual loss functions. For example, consider image classification problem. Given an image, we can using a neural net to predict its label. And we're using an individual loss function, such as cross-entropy loss, to measure the difference between the predicted label and the given label. However, it is non-trivial to solve this unconstrained optimization problem because in practice, we will have millions of data points. And if we want to train a large language model, we have trillions of data points. So which means that even computing the gradient, the full batch gradient is impossible. So that's why we have using a mini batch. So basically, we can only compute the gradient in a subset of data points. The second challenge is that we're often using a large, basically a deep neural net, which contains millions of parameters. Or in this case, if you want to train a ChatGPT-4, you're going to have trillions of parameters. So which means that if we want to design adaptive method, at least non-diagonal case, we need to using a sparse preconditioner. Because here, otherwise, this matrix is a D by D matrix. If it's dense, then it's run on memory. Last but not least, we are compelled to using a half precision or maybe low precision data format because the capacity of a GPU memory. For example, consider a model on 10 billion parameters. So we can only load 5 data points onto the GPU if we're using single precision. But if we're using half precision, we can load 10 data points onto our GPU memory. And we want to load more data points onto our GPU. Unfortunately, using low precision data format increases numerical instability. For example, if you're using non-diagonal methods, we often have using matrix decomposition or matrix inversions. And these operations are numerically unstable and unavailable in half precision. So we're going to talk about 3 key ingredients for designing practical non-diagonal adaptive methods for training large neural net while taking these challenges into account. We're first going to talk about how can we using a cheap curvature approximation to learn a preconditioning matrices. And then talk about how we can reduce the computational cost using inverse-free and decomposition-free update schemes. Last but not least, we're going to present a framework to design fast adaptive methods using structured preconditioning matrices. So let's focus on the part 1. So when we're going to find cheap curvature approximations for neural net training. So let's first of all review Newton's method, because Newton's method is a classical method using curvature informations, and it's a building block for many adaptive methods. So in Newton's method, we're using the Hessian as a curvature approximation. And Newton's method is based on second order Taylor truncation. And when we perform a Newton step, we're essentially doing a local quadratic approximation. In mini-batch case, we consider the following update scheme. So here, we're introducing a new symbol S to represent the full batch curvature. It's also known as a preconditioner or preconditioned matrix. And we're going to use the local curvature information to estimate the full batch curvature or maybe the preconditioner. Here, the Hessian is only computed using a subset of data points. And we're going to introduce a learning way beta 2 to using it to update the preconditioner. The key assumption in this talk is that beta 2 should be very small. So for example, if you're familiar with Adam, the optimizer, if you're using our definition, beta 2 is equal to 10 to the negative 3. So it's very small. Of course, in practice, we're kind of using the Hessian because it's very computer intensive to compute the Hessian, even if we only compute using a subset data points. Moreover, the Hessian is not point definite, so which means that this is a non-convex quadratic. And in this case, Newton method no longer return a local minimum because this is non-convex quadratic, although it still is a quadratic approximation, but it's just non-convex. So in practice, we often consider a gradient outer product as a here. And of course, for many well-known adaptive methods, a square root is also introduced when we update the neural net weights. So in matrix case, we have to using matrix decomposition to compute the matrix square root. So this update scheme is known as RMSProp. So this is we call this update scheme a root-based update scheme. And one of the things that when we're introducing a square root, we're essentially introducing the side descent component. So unfortunately, it's very difficult to understand the role of the gradient outer product due to a square root. Because if you want to using a curvature approximations, we need to figure out whether it's the side descent or the outer product can be used as a curvature approximation. So this motivates us to consider remove the square root from adaptive method. Because in this case, there's no side descent component. Okay. So it turns out that simply removing the square root from RMSProp doesn't work, at least using the original training scheme. We're using a constant learning rate, and also tune all the hyperparameters, including beta 1 and beta 2. So you can see that basically, as you look at these two figures, is that the root-based method basically outperforms the root-free method on convolution neural nets. On transformers, it seems that it's similar, that a root-based method works the best. But is that true? So in fact, we can identify some issues for root-free methods. And if we fix them, in fact, we can make them work, at least for neural net training. First step is that we want to using a non-constant learning rate schedule. So this is a modern training if you want to train neural net. So we usually try to decrease the beta 1 during training. So you can using the classical using the step decay learning rate schedule or using cosine learning rate schedule. And there are more other schedulers. The second step is often overlooked, is that we have to make the update scheme scale invariance. So basically, the idea is that we want to make sure that the update scheme should be invariant, whether the object function is written as a sum of individual functions or average of individual functions. This is very crucial because without making the update scheme scale invariance, now the hyperparameter beta 1 and beta 2 will implicitly depend on the batch size, and which makes the tuning very challenging. And also in our paper, we show that, in fact, the gradient out of product can be considered as a Hessian approximation if the loss can be considered as a normalized negative log likelihood. And as you can see, this should be normalized, so which means that it does matter that whether it is sum over individual loss functions or average of individual loss functions. And we can basically adjust the update scheme for root-free method and make it scale invariance and also affine invariance. So which means solving these two problems should be the same, and solving these two problems is the same. Here, A is a square non-singular matrix. It's just a linear operations. And we can show that, in fact, this is very similar to Newton's method because Newton's method also scale invariance and also affine invariance. So we consider our method as a quasi-Newton method. And I should mention that stochastic gradient descent is not scale invariant and also non-affine invariance. And also, classical method like LBGS is also not affine invariant. So how about the performance? In practice, so in diagonal case, it seems that it works well after fixing these issues. So let's look at the result. So we know that in convolutional neural nets, SGD also usually often outperforms AdaMW, or maybe the root-based method. But if we remove the root from AdaMW, in fact, we can perform as good as SGD. So we can close the generalization gap to SGD on convolutional neural net. And this is because we have no side descent component. But how about in transformers? Because nowadays people want using side descent to train transformers. It turns out that removing the square root doesn't hurt the performance of adaptive methods on transformers. So you can see that, in fact, it performs as well, as good as the root-based method. So there's no side descent component. So this result suggests that gradient of the product itself can be considered as a curved approximation for neural net training, and as well as assume that we can even using the gradient of the product as a curved approximation for non-diagonal methods. So now let's go to the next part, is that how to reduce the computational cost for non-diagonal methods. So let's, Chris, yes.
How do you select the local for your mini batch? How do you select the local?
What do you mean by local?
The local data for your mini batch?
Oh, just randomly sample.
What was that?
Randomly sample the mini batch. Yeah. Okay, so let's talk about how can we reduce the computational cost for non-diagonal methods. So now let's look at some this figure. As you can see that gradient computation dominates the time of optimizing step. In fact, gradient computation takes 90% of the time when we perform an Adam step. So on a very large models. And this is because we're using automatic differentiations to compute the gradient. And automatic differentiation is not for free. So based on this result, we have good news and bad news for non-diagonal methods. The bad news is that classical methods like Newton constant gradient and LBGS are unsuitable for large neural net training because they often require actual function or gradient evaluations. And as we can see that these operations are not cheap. The good news is that we can using non-diagonal adaptive methods because we can using the gradient outer product as a curvature approximation. So there's no actual function or gradient evaluation. And mobile can even make them faster if we can remove the matrix decomposition and also matrix inversion. So let's look at this figure. As you can see that, in fact, non-diagonal methods are useful. As you can see that it can usually converge faster, converge better than its diagonal counterpart if we consider per epoch or per iteration. But they're often overlooked or unpopular because due to the high computational cost if we look at in terms of time. And this is mainly because many existing matrix methods using matrix decomposition or inversions. And these operations are expensive in single precision and unavailable or unstable in half precision. So now let's look at another figure. As you can see that performing one matrix multiplication in half precision is 15 times faster than using one matrix solve in single precision. And it's 100 times faster than doing eigen or root decomposition in single precision. And let me remind you that these operations are unavailable in half precision. So this suggests that we can make, go ahead.
That this claim, what hardware is that?
Sorry?
This claim about
A100.
15x.
A100. So as we can see that, if we can remove, so we can see that by removing the decomposition and inversions, we can make matrix method faster. And we can also support low percent data format. Because, go ahead.
In the previous slides, there is a plot showing the matrix. What do you mean by matrix?
Oh, here is the matrix method.
Like Newton method?
So basically, it's the shampoo.
Oh, okay.
Distributed shampoo method.
Thank you.
Okay. So which means that in fact, we can make the update scheme faster and also support low percent data formats if we're only using matrix multiplications. And this is necessary for training large neural nets because we're often using a single low precision data format.
So, sorry. When you say decomposition free, you're just saying you don't have to compute SVDs, or do you mean something else?
So basically, you can use eigen decompositions, or maybe orthogonal decompositions, QR, LU. So now I need to still reduce the space complexity because non-diagonal is still very expensive, right? Because we're now using non-diagonal matrix. So it turns out that we can using a Kronecker structure to reduce the memory because Kronecker structures can preserve the layout of a given model. So as an example, let's consider a three-dimensional weight tensor used in convolutional neural net. So we often, to learn this weight tensor, if we're using AdaGrad, we often have to flatten the tensor into a vector. Unfortunately, if we flatten the tensor into a vector, we basically destroy the layout of the model. And on the other hand, Kronecker structures preserve the structure of the layout. And as an example, as you can see that in this case, in fact, the Kronecker structures use less memory than the diagonal counterpart. So let's consider when D1 equal D2 equal D3 and equal to 10. So in this case, we can see that the diagonal methods like Adam had to use 1,000 non-zero entries. But the Kronecker case, you can see that we're only using 300 non-zero entries. And this is because we preserve the layout, the model layout. So the quick summary for this part is that, in fact, Kronecker structures as a non-diagonal method with inverse-free and decomposition-free update schemes are time and space efficient. So finally, we're going to present a framework to design such methods. So through Gaussian approximations. So it is challenging to design non-diagonal methods because it's unclear how we maintain the structures if we're using an incompatible curvature approximation For example, consider the precondition is a Kronecker structures, and we want to using a gradient out of product as a curvature approximation. So in this case, this update scheme doesn't preserve the structure. And this motivates us to propose a Riemannian framework. So we will show that, in fact, we can using this Riemannian framework to incorporate arbitrary curvature approximation and handle structure incompatibility and also support arbitrary roots without matrix decomposition. And our method recover Newton's method as a special case. So as an introduction, we were going to show that how we can recover Newton's method. So the first step is to consider a probabilistic relaxation. So given the original function, we're going to re-express the objective function as an expectation using a Gaussian with an infinite inverse covariance or zero covariance. So in this case, the Gaussian becomes a delta function. And this basically is known as a delta evaluation. So we're going to consider a probabilistic relaxation. We want to learn a Gaussian with a finite inverse covariance. So we want to learn both the mean and also the inverse covariance jointly. So the following counter plot shows that, in fact, the optimal solution of this relaxed problem is also the optimal solution of the original problem. This is because the original problem can be considered as a limiting case of this relaxed problem. Okay. So it turns out that this relaxation can be considered as a variational Gaussian approximation when we're introducing the negative entropy of the Gaussian. This is because we can re-express this objective function as a KL divergence between a Gaussian and the original objective function in the exponential space. And in fact, this entropy term is quite optional. With the entropy term, we can recover root-free RMSProp. Without the entropy term, we can recover root-free AdaGrad. And of course, in practice, we're always using the entropy regularizations because we focus on more like generalizations instead of optimization. And we're also using a similar entropy regularizations in optimal transport. So now we talk about the second step is to explore the geometry of the Gaussian. So the key idea is to using the Fisher information matrix of the Gaussian is also known as the Fisher-Rao Riemannian metric. So here is the definition of the Fisher information matrix. And as we can see that, in fact, the Fisher information matrix is high dimensional because here mu is a D by 1 matrix and S is D by D matrix. And D basically is the number of learnable neural net parameters. And we're going to solve these relaxed problems using natural gradient descent. So as we can see, that natural gradient descent is a preconditioned gradient descent where we're using the Fisher information matrix as a preconditioner. And why we're going to using natural gradient descent instead of gradient descent? This is because natural gradient descent is a steeply descent in terms of the KL divergence. And this relaxed problem itself can be written as the KL divergence. And later we'll see that, in fact, there are another reasons why we're using natural gradient descent instead of gradient descent. So in the next slide, we're going to show that, in fact, Newton's method can be considered as a natural gradient descent on the Gaussian. And this is because, at least in the convex case, when the Hessian is become a convex quadratic, we can consider this is a negative log Gaussian. So we're essentially doing a Gaussian approximation in the logarithmic space. But it's equivalent doing the exponential space. Okay, now let's make this connection more clear in the next slide. So we tell that by choosing this particular coordinate system that contains the mean, mu, the inverse covariance S, we can simplify this natural gradient step as follows. Here we have to using a Stein lemma. We're going to talk about the Stein lemma in the next 2 slides. So just bear with me for now. So this is the update scheme to solve this relaxed problem. But we can also use this, we can also adjust this update scheme to solve the original problem simply by get rid of the expectations, evaluate the gradient and Hessian at the mean mu. So basically do the opposite way. So basically we're doing a delta evaluation. And if we set beta equal to 1, we obtain Newton's method to solve the original problem. And if we're introducing an additional learning rate beta 2 to update the preconditioner, we obtain the mini-batch Newton's update scheme. And we can recover root-free adaptive methods by replace the Hessian with the gradient outer product. But so far, we only show that we can recover Newton's method by using these particular coordinate systems. But unlike gradient descent, natural gradient descent is parameterization invariant. So which means we can perform natural descent in another parameter space. For example, we can reparameterize the preconditioner as inverse covariance and then obtain an inverse-free update scheme. So we're going to see an example in the next slide. But let's first try to summarize. The idea is that we have described a procedure to obtain an adaptive update scheme. First step is going to pick a coordinate system of the Gaussian. So in the next slide, so we're going to choosing the Tarski factor of the inverse of S, basically the covariance matrix. Then we're going to perform natural descent in this coordinate to solve the relaxed problem. And finally, we can simplify the natural step to obtain this update scheme to solve the original problem. So now, any questions? Okay. Now let's look at example. How can we maintain structures? So as we see that this is challenging to maintain structures. Here we assume that we can obtain the structures through a reparameterization. So instead of updating S, I'm going to update B. And here this is basically an inverse-free reparameterization. The key idea is that we're going to treat the Hessian of gradient outer product as a partial derivatives. And this is because the Stein lemmas we're going to talk about in the next slide. And then we can using the chain rule to project into this new parameter space. And once we project into this new parameter space, we show that we can perform natural descent in this new coordinate system. And this is structure preserving. And finally, we can reconstruct S back. Of course, this step is completely optional because in practice, we want to compute S inverse. So we just simply replace with B times B transpose. So in practice, we only update, we keep maintaining B without explicitly reconstructing S. So now let's talk about the Stein lemma, because this allows us to view the Hessian as a partial derivatives. So basically, let's look at the second line of the identity. So as you can see that on the right-hand side is the Hessian of the original problem. And on the left-hand side is the partial derivatives of the relaxed problem. So this suggests that we can view the Hessian or any curvature approximation as a partial derivatives. And this allows us to using the chain rule to project the curvature as a partial derivatives into another new parameter space. So the key idea is that basically we exploit the idea is that Riemannian methods are invariant to coordinate changes. So we have shown that we can recover Newton's method by choosing this particular coordinate system that contains the mean mu and the inverse covariance S. We also shown that we can obtain an inverse-free update scheme by performing a natural descent in this new coordinate system that B is the Tarski-like factor of the S inverse. Later we'll see that in fact we can introduce structures in the preconditioner by using a sparse matrix B. But so far all these update schemes are root-free adaptive methods. But we can also, our framework is also flexible that we can incorporate a root-based method. How to achieve that? Consider spectral parameterization or factorization. So here Q is an orthogonal matrix, and D is a vector with positive entries. And because this is and we're going to perform natural descent in this new coordinate system. And because we're using a spectral factorization, we can turn the matrix fractional root into an element-wise root. So this is how we get introducing the fractional root without doing matrix decomposition. So the key idea is that existing method first update S and then do eigen decompositions or matrix factorizations. But we directly maintain the factorizations and learn these factors on the fly. So this is the main idea, how we can get rid of this matrix decomposition. Of course, it's non-trivial to obtain such updates because I can see that perform natural descent, the Fisher information matrix is high dimensional. Here, this is learned number of neural net weights. So in fact, we have the handle constraints, right? Because we also can be, for example, the Q matrix be orthogonal matrix. And also simplifying this the natural gradient is non-trivial because we need to compute the inverse of this Fisher, and we want to use analytical inversions, not using any numerical solver. And the key idea is using we call the local coordinate transformations, and this is basically inspired by Riemannian normal coordinates. And also, it's all share the same spirit of Cartan's method moving frames. So basically, the key idea is that we locally remove the constraints, and then dynamically diagonalize the Fisher at evaluation points. So if you have time, we can talk about these technical details. I'm pretty sure we have time. I'm still pretty have time. Okay. So now we're going to talk about some empirical and theoretical verifications of this idea. So this is our default update scheme. We update S directly, but we can also update the B factor, the choice factors, and then reconstruct the S back. We can also consider spectrum factorizations and then reconstruct the S back using this spectrum factorization. So here is the talk example to show us that if we're using the same sequence of Hessian and series always point definite, in our experiment, we'll use a gradient outer product. Using the same sequence of gradient outer product, the history update scheme, they converge to the same fixed point. And moreover, we can show that in fact this two new update scheme can match the iterate generated by the default update scheme for every iteration. So here the x-axis is the iterations. So this the y-axis basically is the distance to measure the difference between the ground truth and our estimation. In theory, in fact, we can show that these three update schemes are equivalent up to first order accuracy with respect to beta 2. And we assume that beta 2 is small enough. So when beta 2 is small enough, we can consider these three update schemes are equivalent, at least up to first order accuracy. In fact, we can also introduce structures by using a sparse B. And this is because we consider B is a trifactors, so which means it's a non-singular square matrix. And in our case, we don't require B to be a lower triangular matrix. And this immediately knows that this is a general linear group, which basically is a matrix Lie group. So we can construct structures by using his Lie algebra. And if we have time, we're going to talk about the technical details, how we can construct this map. So by using that, by using a sparse matrix B, we can impose structures in his preconditioner. I can also impose structures in his inverse preconditioner. So now let's talk about some results of our method. So we can using a method to train transformers in half precision. And as you can see that from these four figures, that our method performs as good as the existing matrix method in terms of per epoch or per iteration. And as we can see that, in fact, the matrix methods usually outperform the diagonal counterpart. But in terms of time, we can see that our method, in fact, is 2 times faster than the existing matrix methods. This is because our method is inverse-free and decomposition-free. Okay, to do a quick summary before we conclude this talk, and if you have time, we'll talk about the technical details. So we propose a framework, and in our framework, we can view the Newton method as the natural descent on a Gaussian manifold or distribution. And we can view the preconditioner as the inverse covariance of the Gaussian. And we can view the Hessian or curvature approximation as a partial derivatives. And we can use this connection to design adaptive methods by simply replace the Hessian with gradient out product. In fact, you can using more curvature approximations. You don't need to just using gradient out product, because in our case we just treat it as a partial derivatives. And it's flexible because now we can reparameterize the preconditioner as an inverse covariance. And this is because Riemannian coordinate transformations. So to conclude the talk, and then if we have time, go through the bonus slides, talk about technical details. So we propose a framework from a probabilistic perspective, and we can use our framework to design inverse-free, structure-free method for training large neural net, and we support many batch curvature approximations. And we believe that we can use our framework to further unleash the potential of matrix adaptive methods. So do we have time to go through some technical details?
You definitely do, yes.
Okay, sure. Okay.
Can I maybe ask you a question?
Go ahead.
Like, how does this method interact with batch size? Because typically, the smaller the batch gets, like the less realistic the connection to Newton's method will be, because
yes,
the less realistic it is.
But in this case, it's now it's fine because in that case you need using a smaller beta 2. It's just more close to the default update scheme, right? If you're using a smaller batch size, you need to set the beta to very, very small, right? So in this case, the default update scheme is equivalent to update scheme. And typically, this is exactly the key assumption here, right? So basically, we say this is equivalent up to the first order accuracy with respect to the beta 2. If you have very small batch size, you need to set it very small, right? So which means that these 3 updates are essentially just the same, at least up to first order accuracy. So in this case, that is not Newton, it's what we call mini batch Newton method. Any more questions? Okay. So we talk about now we're going to talk about some technical details. So for simplicity, we're going to assume we want to learn the covariance matrix without learning the mean. So in this case, we can consider this map. As later we'll see, in fact, we can truncate it. Because in this case, we assume the manifold, because in this case, this Gaussian with a 0 mean, this become SPD, symmetric positive definite matrices. And basically just a smooth manifold. And we treat this map because in this case, it becomes C infinity smooth. But you can also use a truncation so that it becomes CK smooth. But for simplicity, we assume it's exponential, the matrix exponential map. The key idea is that it's just hard to perform natural descent into this parameterization B, because B must be non-singular square matrix. But we can identify as a Lie groups. Then we can perform natural descent in his Lie algebra. Basically, it's a tangent space. So basically, the key idea is that at each iteration, we're going to construct its tangent space. And then we're going to create a local coordinate systems. So this is the idea of Cartan's method. We're going to create a new so instead of using the global coordinate system, we're going to create a local coordinate system, and this adapt the geometry. And we want to, basically the idea is that we want to construct this coordinate system so that the Fisher information matrix at the current evaluation point become a diagonal matrix. So in this case, become identity matrix. And this is very similar to Riemannian normal coordinates. And then and of course, in next iterations, we need to create another coordinate systems so that we can diagonalize the Fisher information matrix at the evaluation point. So this is how we can simplify the natural gradient step. And then we just take a gradient step, a natural gradient step. In this case, because the Fisher information matrix becomes identity matrix, So natural descent becomes gradient descent in this coordinate system. And then we just project it back to this space. And because this is the matrix exponential map, and we can guarantee this, the updated B is always non-singular, and non-singular is a non-singular matrix. And the key idea is that why this is important is that now we assume S is a dense matrix, but we can also introducing sparse. We can consider structured matrix because now B can be a subgroup of general linear group. Then you can introduce structures, and this naturally link to Riemannian geometry and Riemannian optimization. This is because in Riemannian optimization, so we consider the metric is the affine invariant Riemannian metric, and this basically is equivalent to 2 times the Fisher-Rao metric. So in this case, at least in the dense case, we can compute the Riemannian exponential map. So we have a closed form for the Riemannian exponential map. Then we can define the Riemannian normal coordinate. So here the matrix in this red box is essential because we want to make sure that in this coordinate system, the matrix should become identity matrix, and this is the definition of the Riemannian normal coordinate. So we can simplify and obtain this expression. So instead, we consider generalized normal coordinates. So the main difference is that here, so this is the square root of the orthogonal of the polydefinite matrix S, the preconditioner, or maybe the inverse covariance. In this case, we're using a Trotsky factor of S here. And why we want to using the generalized normal coordinate instead of the Riemannian normal coordinate is because you can see this is a matrix square root, which means this is a symmetric matrices. The product of 2 symmetric matrices is not going to be a symmetric. So which means we do not have a group structure. But if we consider Trotsky factor is a lower triangular matrix, the product of 2 lower triangular matrices essentially is a lower triangular matrix. So in fact, by using a generalized normal coordinate, we manually create a group structure. But why this matters? Because in this case, it's everything dense, we have closed form solution. And also that basically the idea is that in these lower coordinates, basically the Fisher information matrix become identity matrix, and if we're using the Fisher information matrix of this matrix B, it's actually complicated and sometimes can be singular. So which means that I cannot simplify. I can analytically invert the Fisher information matrix if I'm using these coordinate systems. But if I'm using these coordinate systems, I can easily invert it, just identity matrix.
Is M is self-adjoint, right?
Say again?
Is M self-adjoint?
Which one? M?
Yeah, M.
M here? So usually just symmetric matrices.
It's symmetric, yeah, sure.
And you can basically, of course, in practice, this can be singular because you can see, right? So you can look at the degrees of freedoms. S to be symmetric polydefinite matrices. So which means we lose the degree of freedom because it's a matrix, right? So in this case, in fact, we need to restrict the B to be also have the same degree of freedoms. And one way to do that is just make sure the M is a lower triangular matrix. So this is more technical detail there.
Wait, so you're having M be lower triangular, not symmetric?
Yeah, but this is fine. But
so
this
okay. So that's enough to force this. I have to have like a unique inverse.
Yes. The point is that if we don't do that, it's singular. You have to restrict it into lower triangular matrix. At least you need to make sure the dimension, the degree of freedoms match. Otherwise, the Fisher information matrix is going to be singular because you're using an almost parameterized coordinate system. But why this matters that because now we consider it's a sparse case. Consider we construct using a sparse matrix B. So in this case, the Riemannian exponential map and basically Riemannian normal coordinates is unknown because we need to solve ODEs, a geodesic ODE. And this is unknown because we don't know how to solve the ODE. So this is unknown. But this map still remains the same. And now because we have the group structures, now we can preserve structures here because now, for example, you can see there is a subgroup of lower triangular matrix. This is another, lower triangular matrix. They're close on the matrix multiplications. So this is how we manually construct group structures by using a by using a generalized local coordinates. Of course, there's some catch is that in a Riemannian normal coordinates, we can make sure that the Christoffel symbols or the Leibniz-Beta coefficients vanish. But in this case, it's not. But it turns out that for optimization problems, it doesn't matter. So that's what I call is generalized normal coordinates. Yeah, I think that's it. Any more questions?
So I have two questions. So the first one would be, why was the square root introduced in the first place?
Oh, which one? You mean the?
No, in general, like adaptive methods.
Oh, so
what was the initial motivation? It seems to be not so useful.
Okay, so this is a hard question. Actually, I don't know, but if I understand correctly, originally the square root came from AdaGrad papers. They show that basically, if you're using a square root, you can get a convergence bound. In the convex case, because without the square root, you only need to show you can only get a convergence bound on the strongly convexity. But if you're using the square root, you can make it you can remove the strong convexity there. You can change it to convexity.
So there's like a theoretical motivation for
yes.
the bounds, let's say. Okay.
And also, it turns out that in practice works well, but the reason is that because in practice people don't care about whether it's the sum of individual loss functions or average of individual loss functions, and this matters if you want to tune the hyperparameters. You don't want to this hyperparameter implicitly depends on the batch size. So in this case, you cannot set the default hyperparameters, right? Because it depends on batch size.
And if I can have a second question, like you began the talk with like comparing the different optimization methods on different architectures, and there seems to be differences on CNNs versus transformers, LSTMs, you name it.
Yes.
And I wonder like how to think about like how the structure affects the optimization method. And
you mean which structure? You mean the?
I get the structure of the model, like because like LSTMs work very differently to a CNN, and it seems like your type of methods work better on like the model.
So in this case, it turns out it really depends on the curvature approximations and structures there. So the point is that our method that we can use another curvature approximations. You don't need to use a gradient of the product. And if you know PIMs, the physics informed neural nets, in that case, you need to using another curvature approximations. You cannot using. Usually you don't using the gradient of the product. So it really depends on architectures. Go ahead.
I see.
It's a local property that natural gradient descent becomes gradient descent. And can you use this metaphor to put this together?
Sorry, can I say again?
I was like wondering when you mentioned natural gradient descent becomes gradient descent.
So yeah, so
local property.
Yes, exactly. So basically the point is that this exactly is that you're using a Riemannian normal coordinate system. If it's not true, you cannot do it.
So you need the smoothness of the manifold to put it together. So this has to be a real.
Yeah, so that's why in practice you usually should be using a second order or maybe a higher order truncation for the matrix exponential map. And because our goal is try to using an inverse-free update scheme, if you're using the exact exponential map, you still need to do eigen decomposition to compute the matrix exponential map. But if you're allowed to truncate the matrix exponential function, now you can obtain update scheme only depends on matrix multiplications. Yeah, but by doing so, we still is smooth. It's just CK. Any more questions? Cool.
Thank you very much.